I'm going to discuss about this molecular orbital energy diagrams of carbon monoxide and NO, that is nitric oxide. Both of them are heterodiatomic molecules, that is hetero, which is made up of different atoms. The two atoms which are formed here, which are forming a molecule here, are of or different kinds, so we are calling it as a heterodiatomic molecule. Yes. First of all, for the molecular orbital diagram of this carbon and oxygen, that is carbon monoxide, let us first discuss about this electronic configuration of this carbon and oxygen. Yes, it is formed by the carbon combination of this carbon and oxygen atoms, this carbon monoxide. And the carbon, if you can see, its atomic number is 6 and the number of electrons are also 6 here. So the electronic configuration is 1s2, 2s2, 2p2. For oxygen, the atomic number is 8 here. So its electronic configuration will be 1s2, 2s2 and 2p4. So for the formation of carbon monoxide, the atomic number of carbon monoxide is 14. So we've already discussed about this for the systems which are having, or for the molecules which are having the atomic numbers of 14 or less than 14, the order of filling up of this molecular orbitals is where sigma 1s, sigma star 1s, sigma 2s, sigma star 2s. Here first comes pi and then sigma 2px here. So just the reverse in the energy levels of sigma and pi, where the energy level of sigma 2px is more than that of the pi here. We've already discussed this. Then comes this pi star. These two are degenerate levels, 2py and 2pz. Then comes the sigma 2px star. So this is order of filling up of these molecular orbitals from the lowest to the highest for the atomic numbers till 14, whether it is homodiatomic or heterodiatomic, where pi to py and pi to pz are lower in energy than sigma to px. Yes, when we look at this molecular orbital energy diagram for carbon monoxide, this is for carbon, this is for oxygen, where the increase in the energy is this on the left hand side I've shown for the orbitals. For the carbon, it is 1s2, 2s2 and 2p2, where the atomic number is 6 here. And oxygen, it is 8, so 1s2, 2s2 and 2p4. 1s are not shown here, where 1s results in the formation of sigma 1s2 and sigma star 1s2, and 2s for carbon is 2s2, 2p2, 2s2, 2p2 here. Yes. So one electron hidden more here. So yes. And for this oxygen, it is 1s2, 2s2 and 2p4. So when I name this is px, this will be py and this is pz. Again, this will be px, this is py and pz. Here, which orbitals are, the energy of the orbitals in carbon, that is atomic orbitals, is more when compared to that of the atomic orbitals of oxygen here. That is why I've written these orbitals at a little higher level than compared to that of this oxygen here. Yes, see, for the linear combination of these atomic orbitals, it follows the same set of rules as for the homodiatomic molecules. That is, the atomic orbitals which are combining here, that is for linear combination to occur, they should have same energy or almost of the same energy. And the symmetry should also be same, and the overlap should be maximum so that the stronger bonds are being formed. So when we look at for the combination of these atomic orbitals, where 1s will combine resulting in the formation of sigma 1s and sigma star 1s. Here 2s will combine result in the formation of sigma 2s and sigma star 2s. So sigma 2s and sigma star to S. This is bonding and anti-bonding molecular orbital. So 4 electrons here will get filled up here, and for the combination of the where pi are lower in energy when compared to that of sigma. So first 2 energy levels and a single energy level. So here first comes pi, pi 2py, pi 2pz. Then comes sigma 2px. This is pi star 2py, pi star 2pz. Here, this is sigma star 2px. So, the head-on overlap of these px orbitals resulting in the formation of sigma and sigma star orbitals of 2p, and py and pz result in the formation of pi 2py and pi 2pz, and pi star 2py and pi star 2pz here. So, total number of 1, 2, 3, 4, 5, 6 electrons we can see here. So, these 6 electrons here, so these 2 electrons are filling here. So here, 1, 2, 3, 4, 5, 6 electrons. First, this become half filled, then completely filled according to the Hund's rule. Then 2 more electrons will enter into the sigma 2px orbitals. So this is the molecular orbital energy level diagram for carbon monoxide. So if you write the electronic configuration of this here, I can write it as sigma 1s2 here, sigma star 1s2, sigma 2s2, sigma star 2s2, and then comes pi here. So these 2 are degenerate levels, pi 2p y2 and pi 2p z2. Then comes sigma here, sigma 2px2. This is the electronic configuration of this carbon monoxide. When we look at the bond order, that is half into the number of electrons in the bonding molecular orbital minus the number of electrons in the anti-bonding molecular orbitals, half into number of electrons in the bonding. So let's look at for the electrons in the molecular orbitals without the star level. So 1, 2, 3, 4, 5, 6, 7, 8, and 9, and 10. So 10 minus half into 10 minus the anti-bonding. So 1, 2, 3, 4. Since these are not filled, the star level, so this is 4 here. So half into 6, that is the bond order is 3 here. Since the bond order is 3, so the table molecule is stable and it do exist. And what about the magnetic behavior? Since there are no unpaired electrons in this molecular orbitals, we can see this green colored one, this is the last one, all of them are paired up, so it is diamagnetic in nature. So the magnetism is purely dependent upon the number of the unpaired electrons. And this is colorless because there are no unpaired electrons here. So if there are any unpaired electrons, it will have some color, exhibit some color here. So this is, we can see that the bond between carbon monoxide is 3. So how can I write this carbon monoxide here? See, triple bond O, where 1 is sigma and these 2 are pi bonds, we can see them. This is about the carbon monoxide molecule, which is diamagnetic as there are no unpaired electrons and the bond order is 3 here. And it's stable to exist and it is not colored. Right. This is about formation of, molecular orbital energy diagram of carbon monoxide. And if you look at this nitric oxide, that is NO, which is formed by the combination of two atoms, that is nitrogen atom and oxygen atom. Here, yes, for nitrogen, the electronic configuration is, if you can see, it is 7 and 8. So 1s2, 2s2, 2p3, 1s2, 2s2, and this is 2p4. Right. These are the electronic configurations of nitrogen and oxygen in the formation of nitric oxide, that is NO here. And if you look at this atomic number of nitric oxide, that is 7 plus 8, 15 here. So for the systems which are having more than 15, we have already discussed this. The order of filling up of the orbitals is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. First comes sigma 2px. Then comes pi. Pi 2p y and pi 2p z. Just I'm showing the order and not the electrons here. It is this pi star 2py and pi star 2pz, and then comes sigma star 2px. So this is the increasing energy, order of energy of these molecular orbitals for the systems which are having atomic number more than 14 here. That means first sigma comes and then pi here, if you can see here, right? So if you look at this molecular orbital energy level diagram for this nitric oxide, so this is nitrogen and this is oxygen. So the oxygen, you can see the atomic orbitals are little over in energy when compared to that of this s orbital. So I have not shown, so 1s2, 2s2 and 2p3, since atomic number is 7, this is 8, so 1s2, 2s2 and 2p4 here. Yes. So nitrogen 1s2, not shown 1s2, 2s2, 2p3, oxygen 1s2, 2s2, 2p4 here. So 1s2, 2s2 results in the formation of sigma 1s2 and sigma star 1s2, and these 2s orbitals result in the formation of here sigma 2s, that is bonding molecular orbital, sigma star 2s anti-bonding molecular orbital. Here, if you can see that sigma 2p comes first, that is by the overlap of px orbitals here. So 2pz, so this is px, py and 2pz here. So first comes here because it is more than 15, the atomic number. So sigma 2px. This is sigma star 2px, bonding and anti-bonding. Then comes pi here. So I'll show the pi orbitals. So 2, pi, 2. So here it is pi, 2p pi, 2pz, pi star 2py, pi star 2pz. So this one is the molecular orbitals for this nitrogen and oxygen and molecular orbitals of this nitric oxide. So here 2 electrons, so different colored pen here. So 2s, 2 in the filling up of the sigma 2s and sigma sigma star 2s, there are 4 electrons. So let me fill these 4 electrons. And here 1, 2, 3, 4, 5, 6, 7 electrons. So first 2 electrons will go into the sigma 2px. And next here, first degenerate orbitals pi 2py and pi 2pz. So first they become half filled, then become paired up. So 1, 2, 3, 4, 5, 6. One more electron will enter into this pi star level. So this is the molecular orbital energy level diagram of nitric oxide. So if you write the electronic configuration of this, so this will be sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, then comes 2p. So sigma 2p, 2s are finished, so 2p x2 pi. Pi are degenerate orbitals, so 2p pi 2, 2pz2, and only one electron in the 2p pi level, in the pi star. Yes. When you come to the bond order, here half into the number of electrons in the bonding molecular orbital minus the number of electrons in the anti-bonding molecular orbital. So half into number of electrons in the bonding molecular level is 1, 2, so 2s, 3, 4, 5, 6, 7, 8, 9, and 10. Till without the star, we can take the molecular orbitals. And with the star now, number of electrons in the anti-bonding molecular orbitals, that is 1, 2, 3, 4, 5, only 5. So the bond order is half into 5, that is 2.5. See, here one is 1, 2, 3. So pi star here, one electron cancel this, the one electron in one of these pi levels. So bond order is 1, 2, and half of this, so 2.5. So this is molecule. What about the magnetic behavior of it? Since you can see the one electron here, so unpaired electron. So this is paramagnetic in nature. But carbon monoxide was diamagnetic, with where there was no unpaired electron. When you look at the molecular plus, if you can see that the electron from this antibonding will be removed, that is one electron less for NO plus. If this electron is removed from for NO plus, so bond order becomes 10 minus 4, 3 here. So that is how you can write the molecular orbital energy level diagram for NO plus also. Plus, if you like my video, please do like, share, and subscribe my channel. The whole chapter of this chemical bonding has been discussed on my YouTube channel, and the details of this has been given in the description box below the link.